Limiting reactants. When a chemical reaction occurs, the reactants are usually not present in stoichiometric amounts. This is a lot like cooking. If you're going to make pancakes for breakfast, what are the chances, using this recipe, that you only have 1 cup of flour in the house, you only have 2 eggs, and you have exactly half a teaspoon of baking powder? That is not going to happen. The most likely scenario is that you've got a bunch of flour, you've got a whole canister, canister jar of baking powder, and there's only 2 eggs in the fridge, right? Because you're going to run out of something. When we're cooking, there's often one ingredient that limits how much we can make. It's like, you make 5 pancakes and somebody shows up while you're finishing up and they're hungry and they want some pancakes too, and you want to make more, but you can't. Why? You don't have any more eggs. You can't make pancakes if you're missing one of the ingredients, right? Chemical reactions are a lot like recipes. Chemical equations are a lot like recipes. We can take this recipe, and I don't recommend using this to actually make pancakes. You want a couple other ingredients in there as well. But 1 cup of flour, 2 eggs, half a teaspoon of baking powder, you do stuff to them, right? And you're going to get 5 pancakes. And here we have pictures. What if we had 3 cups of flour, 10 eggs, and 4 teaspoons of baking powder? How many pancakes could we make? It's not one that you can just off the top of your head say, oh, this many. How would you figure it out? We need to find the limiting reactant, the limiting ingredient, the ingredient that we're going to run out of. So how do you do that? Well, you look at each of these and you ask yourself, well, if I was able to use up all the flour, how many pancakes could I make? 3. And what you're doing, you could make 3 recipes of pancakes, right? If you have 3 cups of flour, how many pancakes could you make? 15. Because you can make 5 pancakes for every 1 cup of flour. That's like a mole ratio, but with a recipe. So that would get us 15 pancakes. Well, with 10 eggs, how many pancakes can I make? Well, I get 5 pancakes for every 2 eggs, right? 5 pancakes for every 2 eggs. What does that get me? 25. So I can already tell it's not going to be the eggs, right? 4 teaspoons of baking powder. 4 tisps. I'm going to call this BP. The recipe says I can get 5 pancakes for every half teaspoon. Half is 0.5 tisps of BP. That's one you might want to do on your calculator, right? 4 times 5 divided by 0.5, 40. We got enough baking powder to make 40 pancakes. Can we make 40 pancakes? No, because we're going to run out of something. So we're going along, we make pancakes, we make 5 pancakes, we make 10 pancakes, we make 15 pancakes, and pancake making has to stop. Right? We ran out of flour. How can you make pancakes without flour? You're done. We figure out what our limiting ingredient is by asking ourselves, how much product can I make if I use up each of the ingredients that I have? The smallest one is the number of pancakes we can make, and the ingredient that gave us that smallest number is the limiting ingredient. Does that make sense? Usually the pancakes make sense. And then we move into chemicals and you're like, what? Just remember the pancakes, it'll be okay. So if this was a chemical reaction, we would say that the flour is the limiting reactant. That limits how much product can be made. And the amount made by the limiting reactant is the theoretical yield. If you set out to make 15 pancakes, do you always end up with 15 pancakes? Sometimes you get a little exuberant in flipping it and it goes on the floor, right? Or you turn your head and the dog steals one off the plate. Stuff happens, right? But in theory, you could make 15 pancakes if everything goes perfectly, right? So we need to do this same process when we're talking about chemical reactions, because just like when you're cooking, it's very unusual to have stoichiometric ratios in your reaction flask or your reaction vessel. Usually, you're going to have one ingredient, one reactant that runs out. When that reactant is gone, the reaction has to stop. Just like when the flour was gone, we had to stop making the pancakes. I'm getting hungry now. So these are the steps. And when do you need to do this? Whenever they give you the quantity of more than one reactant. So part of the problem is just recognizing, is this a problem where I have to deal with a limiting reactant? If they give you the mass of 2 or more products, then yes, you do. And the way you do it is you calculate the amount of product that can be made from each reactant. And then you look for the one that gave you the smallest amount of product. That's your limiting reactant. And that smallest amount of product is the most that you can make. You can't make any more, even though you've got extra eggs and extra baking powder. You can't make any more pancakes because one of the ingredients is gone. When one of the reactants is all used up, the reaction stops. That's called the theoretical yield. That's the maximum amount of product that can be made. So let's do an example. Here's a very simple one, making salt from sodium and chlorine. If we have 53.2 grams of sodium and 65.8 grams of chlorine, what are the limiting reactant and the theoretical yield? Again, I'm going to use my chemical equation to organize the information here. They're telling me I've got 53.2 grams of sodium, 53.2 grams of that one, and 65.8 grams of chlorine. What's the limiting reactant? What's the theoretical yield? Well, there's only one product here, sodium chloride. So what we're trying to find out is how much sodium chloride can we make? And that should probably be in grams. So what we're going to do now is we're going to do 2 stoichiometry calculations. Grams to moles to moles to grams, and grams to moles to moles to grams. All right. One, we're going to start with the sodium and figure out how much sodium chloride we can make. The other one, we're going to start with the chlorine and figure out how much sodium chloride we can make. Exactly like what we did with the pancakes. We took the amount of flour. How many pancakes could we make from that? You do that for all of the ingredients, all of the reactants, and then you look at the amount of product and you just pick the smallest one. So the path for this first one is grams of sodium to moles of sodium to moles of sodium chloride to grams of sodium chloride. 53.2 grams. 53.2 grams of sodium times moles of sodium We got moles of sodium chloride and grams of sodium chloride. All the units in place, then we look for numbers. The middle one, the mole-to-mole ratio, comes from the balanced chemical equation. 2 moles of sodium give 2 moles of sodium chloride. 2 moles of sodium chloride for every 2 moles of sodium. Could you reduce the fraction? Sure you could. Do you have to? No. I like to just write down the coefficients. How do we convert grams of sodium to moles of sodium? We're going to look at the wall, right? Periodic table. Find the molar mass of sodium. 1 mole of sodium weighs 22.99 grams. And then we need the molar mass of sodium chloride. So sodium was 22.99. And chlorine is 35.45. And if I remember correctly, that's 58.44. One mole of sodium chloride weighs 58.44 grams. So 53.2 times 1 divided by 22.99 times 2 divided by 2 times 58.44. $135.23 grams. I'm thinking about significant figures. I've got 3 here and 4, exact and 4. So this is going to have 3 significant figures. I just wrote down the 2 extras before I rounded off. If I can use up all the sodium because there's plenty of chlorine, I can make 135 grams of sodium chloride. Any questions? Now we're going to do a very similar calculation. But instead of grams of sodium, we're going to do grams of chlorine and moles of chlorine, and then go to moles of sodium chloride and grams of sodium chloride. So 65.8 grams of Cl2. Moles of Cl2. And then moles of sodium chloride. And moles of chlorine in the bottom. Grams of sodium chloride, moles of sodium chloride in the bottom. It's similar, isn't it? But it's not quite exactly the same. So this mole ratio in the middle, there's still a 2 in front of sodium chloride. The chlorine has an implied 1. So here the ratio is 2 to 1. I need the molar mass of chlorine. That's going to be the 35.45 times 2, because it's Cl2. So 70.90. And this last one, that last term is exactly the same as the first one. It's grams of sodium chloride to moles of sodium chloride. So we don't need to do any more calculations. We just have to copy that one down. 65.8 divided by 70.9 times 2 divided by 1, if you like, times 58.44. Again, this number is also going to have 3 significant figures, 108, 0.47 grams of sodium chloride, which we would round to 108 grams of sodium chloride. So how much salt can we make? 108. We've got two answers here. We picked the smaller one because we're going along making sodium chloride. We make 100 grams and 105 and 108, and bang, the reaction stops. What ran out? The chlorine. So you do the two calculations. You identify the smaller, that's this one. That's our theoretical yield. TY, theoretical yield. And then just run back to see what you started with, the Cl2, that's our limiting reactant. Limiting reactant. Any questions? You can't tell that by just looking at the masses that you start with. We had more chlorine by mass than sodium, but this ends up running out first because chlorine molecules weigh a different amount than sodium atoms do. And we need twice as many sodium atoms as we do chlorine. And so there's these different factors going on in here, and so you can't just look at it and decide. There's the scary problem from the book. Blah! Alka-Seltzer tablets contain aspirin, sodium bicarbonate, and citric acid. When they come into contact with water, the sodium bicarbonate and citric acid react to form carbon dioxide gas, among other products. The formation of CO2 causes the trademark fizzing when the tablets are dropped into a glass of water. An Alka-Seltzer tablet contains 1.7000 grams, thank you, of sodium bicarbonate and 1.000 grams citric acid. Determine for a single tablet dissolved in water which ingredient is the limiting reactant, what mass of the excess reactant is left over when the reaction is complete, and what mass of CO2 forms. Well, this stuff up here, all very nice and everything, but we don't really need that. We don't really need to know about this. Let's make that a little bigger. I'm just going to clear up some space here. Let's take the numbers and organize them. So 1.7000 grams of sodium bicarbonate. Bicarbonate is a different word, different name for hydrogen carbonate. So this is the sodium hydrogen carbonate or sodium bicarbonate. So it's telling us that we have 1.7000 grams of that, and that it has 1 gram of citric acid.